The moon looks calm from Earth, a pale disk, familiar enough to ignore. But up close, it's not a world. It's an exposed surface in open space. No sky, no shelter, no mercy. Every horizon is a line drawn between sunlight and lethal cold, between silence and invisible radiation, between ancient rock and the constant possibility of impact. And yet, in the coming decades, a permanent human foothold there is no longer science fiction. It is a plan, sequenced, engineered, and increasingly tested by machines. Not a flag and footprints visit, not a 3-day expedition, a sustained presence, infrastructure, power, habitats, possibly even an underground expansion, turning the moon from a destination into a place. China's lunar strategy is often described as building a base, but that word is too small for what's being attempted. This is closer to the first chapter of an off-world settlement project. Robots first, then structures, then people, living not only on the surface, but eventually beneath it. What makes the story compelling isn't just ambition, it's the environment itself. The moon doesn't resist life with drama. It resists with physics. Start with the simplest problem. There is no air. On Earth, an atmosphere does more than provide oxygen. It spreads heat, softens temperature swings, slows micrometeorites, and gives every structure an external pressure to push against. On the moon, there is only vacuum. That means any human habitat must carry its own breathable atmosphere like a fragile bubble. Every seam and seal a potential failure point. Then comes temperature. With no atmospheric blanket to distribute warmth, the lunar surface behaves like a material left directly under a blowtorch and then plunged into a freezer. In sunlight, the ground can climb above 120 degrees Celsius. In darkness, it can fall far below freezing, and the day-night rhythm is unlike anything humans evolved to endure. The moon rotates so slowly that a single location can experience about 2 weeks of uninterrupted daylight, followed by about 2 weeks of night. Light itself becomes a hazard. Sunlit metal overheats. Shadows become cryogenic traps. The border between them, the terminator, is a moving edge where conditions can change brutally across short distances. But temperature is only the beginning. Beyond Earth's magnetic field, space is filled with energetic particles from the sun and from distant cosmic events. Earth's global magnetosphere and thick atmosphere blunt much of that radiation before it reaches the ground. The moon has no comparable shield. Its surface is a target, continually exposed. That exposure turns time into a weapon. A short visit may be tolerable with careful planning, but long-term residence demands serious protection. And then there are impacts. Look at the moon through a telescope, and you see the scars, craters upon craters, layered across billions of years. Those are not relics of a violent youth alone. They're evidence of an ongoing reality. Space debris and micrometeorites strike the moon frequently. On Earth, most small objects burn up in the atmosphere. On the moon, the vacuum offers no friction, no braking, no warning. The surface is bombarded by natural shrapnel, and the only defense is shielding, redundancy, and the acceptance that some risks cannot be eliminated, only managed. This is why early lunar habitation was brief. Humans have stood on the moon before, but only for short stretches measured in days. A permanent outpost means solving problems that short missions could outrun with haste. The cold, the heat, the radiation, the impacts, the loneliness. The engineering reality of keeping a small pocket of Earth alive inside a world that is not alive at all. Before you build for humans, you test life in miniature. One of the most revealing steps in China's recent lunar work wasn't a grand habitat prototype. It was something smaller and more fragile, a sealed biological experiment, a tiny artificial ecosystem sent to see whether living organisms could persist, even briefly, on the moon. Inside, there were the ingredients of a simplified biosphere, plant seeds and small life forms meant to represent a basic cycle: growth, respiration, survival. For a moment, it worked. A sprout emerged, new leaves formed, an image as symbolic as it was scientifically valuable. Life attempting to take hold where it never naturally evolved. But the moon is a place that punishes delays. Within days, the experiment failed. Not because the concept was foolish, but because the environment was relentless. Temperature swings alone can overwhelm a closed system. Without heavy insulation and robust thermal control, internal conditions drift toward the extremes outside. Radiation, too, becomes a background stressor, especially for long exposure. The result was a blunt lesson delivered in a matter of days. Survival on the lunar surface is not a matter of simply bringing life there. It is a matter of constructing an entire protective world around it. That failure wasn't wasted effort. It was reconnaissance of a different kind, proof that the moon's hazards are not theoretical. They are practical constraints that shape every design choice from this point forward. So the strategy pivots to what space does best, using machines as the first residents. Robots don't need oxygen. They don't fear isolation. They can be built with radiation-hardened electronics, wrapped in shielding, and sent into places where human beings would be gambling with their lives. If a robotic mission fails, it is expensive and painful, but it is not a funeral. And in the lunar program, robots aren't just scouts. They are intended to become builders. The overall approach can be understood as a three-act progression, each phase unlocking the next. The first phase is reconnaissance, mapping, sampling, and characterizing the terrain and resources. Where is the ground stable? Where are the best landing zones? Where does sunlight persist long enough for power systems? Where might water ice be accessible? Which regions offer natural shelter? This is not exploration for curiosity alone. It's surveying for construction. The second phase is infrastructure, turning knowledge into hardware. This is where robots stop being visitors and become workers, moving regolith, preparing surfaces, manufacturing building material, laying down pads and roads, assembling modules, and proving that an outpost can function before a human ever arrives. Only after that comes the third phase, human habitation. The logic is unforgiving but sensible. You don't send people to set up camp in a vacuum world if you can send machines to build the camp first and test it, while humans remain safe at home. In this plan, the moon is approached the way engineers approach any extreme environment: measure first, build second, inhabit last. Launching a complete base from Earth sounds straightforward. Fabricate everything on the ground, load it into rockets, land it intact. But mass is tyranny in spaceflight. Every kilogram requires fuel, planning, and risk. The larger the payload, the harder the landing, the more complex the hardware, the more fragile it can be when it finally arrives. So the more sustainable path is to build with what's already there. That concept has a name in space engineering, using local materials to support local operations. On the moon, that material is regolith, the crushed rock and dust that blankets the surface. It's abundant, but it is not friendly. Abrasive, electrostatically clingy, and chemically reactive in ways that can degrade machinery and seals. Still, it's the one resource that exists in near limitless quantities. The goal is not merely to use regolith, it's to turn it into infrastructure: bricks, shielding, landing pads, roads, and eventually structural shells around pressurized living spaces. Two main construction philosophies emerge. One is brick-based fabrication. The process resembles an automated brickworks, except the raw feedstock is lunar soil, and the workers are machines. Regolith is collected, packed into molds and heated to high temperatures to sinter it, essentially baking it until particles fuse into solid forms. These blocks could be stacked into walls, arches, and protective berms. They could also be arranged into surfaces that matter hugely on the moon. Stable landing pads that reduce dust blowback and prevent rockets from blasting craters into loose ground. This kind of mass, thick, stone-like shielding does something extremely valuable on the moon. It blocks radiation. It absorbs impacts better than thin metal shells. It buffers temperature swings. It becomes the outer armor of a human habitat. But there is a catch, and it is fundamental. Humans can't live in a stone pile unless it can hold pressure. A lunar habitat must be pressurized like a spacecraft, and pressure is relentless. It pushes outward equally in every direction, searching for weakness. This is why many pressure vessels, tanks, submarines, spacecraft modules favor rounded shapes. Curves distribute stress, corners concentrate it. A rigid, rectangular structure made of blocks can be excellent shielding, but it is not naturally a pressure vessel. To make it a home, you likely need an inner liner, something smooth, sealed, and curved inside the protective outer shell. In other words, a habitat within armor. The second philosophy is additive construction, a printed structure built from processed regolith. The advantage is geometry. Instead of stacking blocks into a box-like wall, printing allows continuous curves, domes, and forms that cooperate with pressure rather than fighting it. Designs can mimic nature's solutions: shells, arches, layered ribs, structures that achieve strength not by brute mass alone, but by distributing forces intelligently. Yet printing regolith comes with its own compromises. Lunar soil is not a ready-made ink. It must be processed, often heated, transformed, and in many proposals mixed with binders that may need to be imported from Earth. That reduces self-sufficiency at first. It also adds complexity: thermal control, material handling, precision motion in dust-filled vacuum conditions. Still, if the engineering can be made reliable, printing offers a vision of lunar construction that scales. Taller structures become plausible in lower gravity. Wind is irrelevant. Weather does not exist. A printed shell can become both shield and habitat, an outer skin built from the moon, enclosing an inner atmosphere that humans can breathe. These are not competing fantasies. They are complementary tools: brick-like mass for shielding and infrastructure, printed shells for pressurized volume, roads and pads first, then protective walls, then habitable cores. But none of it works without power. On the moon, energy is not a convenience. It's survival. Power runs life support, heating, cooling, communications, lighting, water processing, oxygen generation, robotics, excavation, manufacturing. Every one of those needs a steady supply of electricity, and the lunar environment makes steady power hard. Solar energy is the obvious option, and in some regions, especially near the lunar South Pole, there are areas that can receive long periods of sunlight. But even then, darkness is never completely avoidable, and for much of the moon, night lasts about 2 weeks. Storing enough energy to bridge that gap is difficult. Batteries scale poorly when you need continuous, high-power operation. This is why nuclear power repeatedly appears in long-term lunar planning. A reactor offers something the moon otherwise denies: uninterrupted power. It does not care if the sun has set. It can sustain industry and life support through long nights and emergencies. And the moon offers an environment that, in some ways, simplifies aspects of reactor operation, especially if the system is placed in permanent shadow or shielded terrain where heat rejection can be managed carefully. Nuclear power also reframes construction timelines. If you have abundant energy, you can melt regolith, sinter bricks, run printers, operate excavators, and keep habitats stable. Without it, every task becomes rationed, delayed, and fragile. Energy is the foundation of permanence. Before the moon can be lived on, it must be powered. The most dramatic shift in lunar settlement thinking happens when you stop treating the surface as the only option. The moon has scars not just on top, but underneath. Ancient volcanism, when the moon was warmer and geologically active, may have carved out vast lava tubes, long, hollow tunnels left behind after lava flowed and drained away. On Earth, lava tubes can be stable, cathedral like caves. On the moon, with lower gravity and no erosion from wind or rain, such structures could be even larger and better preserved. We know where to look because there are places where ceilings appear to have collapsed, leaving circular openings, skylights, into darkness. These are hints of empty space below. For settlement, the appeal is immediate. Underground, you gain what the surface refuses to provide. You gain radiation shielding measured in meters of rock, not millimeters of metal. You gain protection from micrometeorite impacts. You gain thermal stability. The wild surface swings are damped by insulation. Inside a lava tube, the moon's brutality becomes quieter, steadier, more manageable. Of course, living underground introduces new problems: access, lighting, structural reinforcement, dust control, the logistics of moving equipment and people through confined geometry. But it also opens a path to a more resilient colony, a place that doesn't merely survive on the moon, but uses the moon's own geology as shelter. Robotic missions equipped to probe the subsurface using techniques such as ground-penetrating radar are critical here. You cannot build into what you cannot map. The underground is not just a destination, it's a survey challenge. Find the voids, measure their stability, identify safe entry points, then decide whether the first true lunar city is not a cluster of surface domes, but a settlement hidden beneath an alien ceiling of basalt. The most important detail about a lunar base is that it isn't built in one trip. A permanent outpost is assembled across a sequence of missions, each landing delivering parts of a larger system: power generation, communications, robotic work crews, resource processing equipment, scientific instruments, and eventually habitats rated for human life. A plausible roadmap places the first major construction push in the 2030s, with early missions establishing the essentials before any long-duration crew commits to living there. The earliest stages focus on a command and support nucleus: power, communications, navigation aids, and robotic operations capacity. Later stages bring research capability, resource utilization, surface mobility, sample collection, and the beginnings of a broader scientific presence, turning the base from a camp into an instrument of discovery. The South Polar region becomes especially attractive in this context because of the possibility of water ice locked in permanently shadowed craters. Water is not just for drinking. It can become oxygen. It can become rocket propellant. It can become shielding. On the moon, water is infrastructure. By the time humans arrive for sustained stays, the goal is no longer to prove that people can land. It is to prove that people can remain. Because staying changes everything. A settlement forces repetition, routine, maintenance, repair, human health in low gravity, psychological endurance in isolation, the slow accumulation of small failures that can become catastrophic if ignored. The moon is not a place where you can call for help and expect it to arrive quickly. It is a place where the margin for error is engineered, not hoped for. If the 20th century's lunar story was about reaching the moon, the coming chapter is about whether we can be changed by it and whether we can change it in return. The moon offers no forgiveness, but it offers something rare: a nearby proving ground for living off Earth. The technologies required, autonomous construction, closed loop life support, in situ manufacturing, long term radiation shielding, reliable power, are not lunar technologies alone. They are the foundation for any future beyond this world. And yet, the moon will not be conquered by declarations. It will be negotiated with materials, with energy budgets, with sealed habitats that must hold pressure every second of every day, with robots that must work in dust and vacuum, with human beings who must endure a landscape where a single step outside is instantly fatal without protection. A city on the moon may begin as a few machines in the polar silence, assembling walls out of gray soil. It may expand into domes and tunnels, into buried corridors that never see the sun. It may become a place where instruments stare outward into deep space and where humans look back at Earth as a bright, distant world. Or it may fail again and again until the engineering catches up with the ambition. Either way, the moon is no longer just an object in the sky. It is becoming a destination with consequences. And the question is no longer whether we can reach it. The question is what it will cost to stay.